section 2.3 is really dark, isn't it? Is that better? What do you guys want? Off or on? On? Okay. All right, 2.3 is other set operations. We're going to take a look at, I think it's 4 set operations. Maybe not all today, but in this section anyway. Okay? So the first set operation that we're going to take a look at is set intersection. Set intersection is the set of elements that are common to both sets. It's exactly what we mean when we talk about the intersection of 2 lines. It's where they cross. And the intersection of the streets, right? Kickapoo, MacArthur out here. The intersection is exactly it's like a square in the middle where they cross, right? They've got it all like separated out now with a brick, don't they? Yeah. The intersection is where they cross. So notationally, I want to show you what that looks like with our sets. So we have A intersect B. So intersection looks kind of like an N. That's the symbol for intersection. And in terms of notation, and I'll draw you a picture too, this looks like all x such that x is an element of A and x is an element of B. Now over on the side of your paper you have a little bit more space. My spacing on my screen is a little bit different. But we're going to draw a Venn diagram for what intersection now looks like. Okay, so we've got our rectangle, that's our universal set. So this is U here. And inside of our universal set we have 2 circles. And we're drawing them as though they are in fact related to get the diagram to look, to show where it would have an intersection. So one of them is set A. The other one is set B, and the intersection is what they have in common, which means it's what? Yeah, the sliver in the middle, right? It's this piece right here. That's the intersection where they overlap. All right, let's do union now. So the set union is the set of all objects where they're in one set or the other set or both. Okay, so notationally, it looks like a U. So U for union, N for intersection. And this is a set of all x such that x is an element of A or x is an element of B. And we don't really need to write or both, but it could be both, and that would be okay. Okay, a Venn diagram for this, we would have a circle for A and a circle for B. And here's my universal set. And inside of this circle, we have everything shaded in. We get it all. Okay, so I talked about intersection, physical description, intersection of 2 streets. You have a physical description of union as well, but you may not be aware of it. A union is like when you get married, right? When you get married, the preacher says something like, for better or for worse, for richer or for poorer, and in all of that it says, I get all of your stuff and you get all of mine, right? Everything that I have now belongs to you, and everything that you have now belongs to me. It's a union. It's a merging of everything, okay? So what happens when people get married, especially when they're older, is they've already set up these households and we have to merge 2 households. So now we all of a sudden have 2 crock pots, right? 2 blenders and 2 of everything, right? So we get a collection of things where we merge it all together. Okay, that's a union, and that's what we're getting in terms of this picture. And that's actually where we end up on our first example. I'm sorry, one more before we get our first example. I'm getting ahead of myself. Here's our third type of relationship operation today, and this is relative difference. Relative difference is the set of all elements in one set that are not in the other one. And it looks like subtraction. So it looks like A minus B. And this is the set of all x such that x is an element of A and x is not in B. You can write the word and between them if you want. The comma sort of means and, but Both things have to be true. So a picture for this one. Okay, so remember, you have to have the item inside of A, but it can't be inside of B. So our picture is this moon shape here on the left. We get the outer part of the circle A, but not the part that overlaps with B. Okay? All right, now we're going to take an example of a couple people who are getting married or have gotten married. I don't remember how I phrased it. Let's see. Consider Mary, single mom to one child, Mark, and Joe, single dad to two children, Jack and Jill. Mary and Joe get married. Together they have two children, Ann and Andy. If M is equal to Mary's kids and J is equal to Joe's kids, find and describe the following. And I'm not intending to indicate anything about relationship and them not being all their children, okay? So don't read too much into what I'm doing here, okay? So think of it as biological child, and then we're all good to go. Sound good? All right, so M is Mary's biological children, J is Joe's biological children. So what would M intersect J look like? Who would that be? That would be Ann and Andy. So this would be the kids they share, they have in common, that they're both the biological parents for. And in our situation here, that's Ann and Andy. What would M union J be? All of them. We get everybody. Let me say all kids. Okay, so the union is like the family picture, right? Everybody gets to be in the family picture. That's what a union is. So we've got, who did we start with? Mark? No. Yes, Mark. That was Mary's son. And then we had Jack and Jill, which were Joe's kids that he brought into the marriage. And then we have Ann and Andy born afterwards. So what would M minus J be?
Just Mark.
What would it be?
Just Mark. Right?
Okay, yeah. So it would be Mary's only. The ones that Mary only is the parent for, right? Joe's not a parent for any of these children, and that would in fact be Mark. It's the kids she brought into the marriage with her, Mark. It's just because we described them as the kids.
Oh, okay.
Yeah. So if we were describing Mary's family or Joe's family, we would. Yeah.
Okay.
Yeah, that's a good question. So this is like the movie, right? Yours, Mine, and Ours? Something like that. Okay. All right, some properties of sets. Commutativity, associativity, and distribution. So let me show you what these look like. Commutativity is the idea that the order of something doesn't matter. That's what commutative means. So it says something like this. So for all sets A and B, this is going to be true. A union B is equal to B union A, and A intersection B is equal to B intersection A. It doesn't matter if we talk about the union of Kickapoo and MacArthur or the intersection. The intersection of Kickapoo and MacArthur or the intersection of MacArthur and Kickapoo, right? It's the same place. It doesn't make any difference which one I said first. It doesn't make any difference when we were looking back at the other example if we were talking about Joe and Mary or Mary and Joe's kids, right? It's the same description either way. Doesn't matter on the order of that. Associativity. So this is again for all sets. Oops. A and B and C. So this says that the A intersect B intersect C, is the same thing as A intersecting B intersecting C. So the order in which we do the intersecting doesn't matter. We'll get the same result either way, and the same is true for union. A union B union C will equal A union B union C. And the last one is distribution. Okay, so we have the same for all sets A, B, C. And this one actually is a statement that combines unions and intersections into the same statement. So A intersect B union C is equal to A intersect B union A intersect C. So I can either look where the two intersections are and then find their union, or I can look where the union is and then find its intersection with A. All right, the next slide has a very important formula. It will help us to solve Venn diagrams as we move on into this section later. So this is called the cardinal number formula. And I'm going to show it to you first, and I'm going to show you why it works with a picture. So this is like proof by picture, which isn't exactly a proof, but at least gives us a justification. If we are trying to find the number of items in a union, we can find the number of items in one set plus the number of items in the second set. And then we subtract the number of items in their intersection. And I want to justify for you why this works, or why it makes sense with a Venn diagram. So here's our universal set in our rectangle. We have our two sets A and B. And if we were to count everything inside of circle A, and we'll do it kind of like a shading, okay? I would get everything in A shaded in, correct? And then if I count up everything inside of circle B, I get all of this. What do you notice happened when I counted those two things? I double counted what they had in common, right? The same thing would happen if I went back to this example with Mark and Mary. Mark and Joe, sorry. Mark's the kid. Mary and Joe. Whoever the parents are. We're going to talk about them for a second. Count for me. How many kids? What's the cardinality for M? How many kids are Mary's? 3, right? It's 3.
She only brought one.
She had Mark, and then she had Ann and Andy. How many kids are Joe's? 4. There are not 7 kids, though, correct? Right? That's what I would get if I added 3 and 7 together. Why would I be getting 7? Because I counted Ann and Andy twice. So that's what's going on with this cardinal number formula, is that we have to subtract the intersection because we're removing the double counting. Okay? All right. We have one more example, and then we'll stop for today. This is our last set operation, actually. It's called a Cartesian product. The Cartesian product is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. And you know a very common Cartesian product. Do you know what it is? Do you know what you called it?
The points on a graph.
Yeah, the points on a graph, the xy coordinates on an xy plane, right? In fact, we call it a Cartesian coordinate plane. That's where the name is coming from. So you're taking all of the items that move left and right. That's our x values. All the items move up and down. That's your y values. And it matters what order it's in. You get a different location on the plane if you're in a different place. Let's just do a real quick example so I can show you how this would work if it's not necessarily the Cartesian coordinate system you've seen before. We have a set A, and we're going to let that set be x, y, z, just 3 elements. And we'll take the set B, and so as not to confuse the issue, we'll just put numbers in here as 1 and 2. So we remember where we're collecting a number from versus where we're collecting a letter from. And what we're going to do is we're going to find the Cartesian product, and the Cartesian product really looks like a product, like multiplication, A cross B. Okay? And what we're going to get is we're going to get a collection of ordered pairs. So everything I put in here is going to be in a set like a XY ordered pair. It's going to look like when you're working with a, graphing. Okay? The first item has to come from set A, so maybe like X, and the second item has to come from set B, so maybe like 1. This would be one of my ordered pairs. Can you give me another one? X2. What's another one? Y1. And Y2. What's next? Z1. I always put a line through my Z's because otherwise they look like 2's. And the other one would be Z2. Okay, so the first thing is if you're asked to find the Cartesian product, you're being asked to find all the ordered pairs. That's what that means. Okay? Now, I want to show you a cool notice kind of thing. Notice. This is one of those, we're going to do it as a conjecture. It is a true statement, but we're not proving it. We're just showing it from an observational standpoint. Can you tell me how many items are in A cross B? What did you just find? 6. How many items are in A? 3. And how many items are in B? 2. What does it appear happens?
Looks like you're multiplying.
Yes. It looks like if you multiply these two together, you get the result up here. And in fact, that's a true statement. The number of items in the Cartesian product is equal to the number of items in set A times the number of items in set B. So if you're trying to figure out, did I get them all, right? You should at least be able to count them up and check and make sure that you did in fact get, the right number, right? Should have 6 items there because there's 3 items in set A and there's 2 items in set B. All right, we will stop there for today.